My name is Paul Lewis. I work for Engineered Air Balance out of the Dallas office. Today we're going to be going over a case study of testing, adjusting, and balancing a hyperscale data center. I'm thinking this talk is going to be about 40-45 minutes. We're going to have some time at the end for a few questions. We have some pretty interesting, new testing procedure in this that I've never seen before. So hopefully we'll have enough to talk about with that. This presentation will provide a case study testing at a hyperscale data center. TAB process, like any job, can differ significantly from project to project. In this case study, we'll talk about how our TAB process evolved over the life of the project. We're going to be talking about the case study. We'll examine a 2.5 million square foot campus located in Fort Worth, Texas, consisting of 6 buildings, housing 22 data halls, a cold storage facility, 3 admin areas, 2 central plants, and 2 industrial water plants. This project was one of the largest fan array systems we ever had the pleasure of testing. Each hall has a built-up system consisting of 12 fan arrays of 15 fans each, delivering approximately 1.17 million CFM. Oh, yes, at the end of this course, you guys, like I said, we're going to be talking about what's different at a TAB that we're doing at a hyperscale data center versus how it differs from other projects. This right here, understanding the fan array airflow verification TAB procedure that improve our testing time. That will be the majority of probably what I talk about today. And hopefully we'll get to these last 2 things, understanding the TAB's role during hydronic testing, and then understand how TAB and a CXA can work together during L3 and L4 commissioning. All right, so let's total system balance. We got to talk about that since we're ABC. So what we're going to do in a data center, testing and balancing the HVAC system to operate at optimal level. We're also focusing on verifying the control systems, sequence of operation testing to operate at optimal level, and verifying the sensor calibration to operate at optimal level. Like I said, all these will fit within the 5 levels of data center commissioning. So commissioning for this building was completed by areas. When I started at this project, I had never heard of the 5 levels of data center commissioning. So kind of go over that right now. Level 1, factory witness testing. So owners, contractors, engineers visiting the site, visiting the manufacturer, looking at equipment, deciding if there's anything to be changed with the design. We weren't a part of that, so I'm not going to talk about it too much. The level 2 is site acceptance and inspection. So equipment gets dropped off, checking the nameplates, making sure the right equipment's there. L3, pre-functional testing. L4, functional performance testing. That's where you guys come in, really do a lot of the testing of the systems, the sequences. And then L5, integrated system testing. So everything working together. So like I said, TAB, during the L2, we'll do a walk, check out the equipment, make sure everything is in the right spot, valves, dampers, for the few dampers that we do touch, make sure the equipment's going the right way, make sure everything's spinning the right way. L3 is where we do the most of our testing. So during L3, the mechanical, electrical will start up the equipment. The controls group will come in and do their own sequence testing, their point-to-point, and then we'll come right there at the end when those 2 things are done and bring it all together. During L4, when you guys, your CXAs are coming in, we'll deliver a preliminary test report to you and be available to assist the CXA. Most of these all have checklists that we're looking at. Pretty by the book. You got to go step by step. For our TAB, we didn't have a checklist. That was from the owner. So we kind of were able to kind of play in our own little zone a little bit and able to test it like we thought we needed to. Run through what a typical data center looks like. So bear with me. We're going to get through this, and then we'll start talking about some of the cool stuff that we found. The critical areas at our data center, we have 4 data halls, each with limited design airflow. 12 what we call air handlers. They were all built up right there on site. The equipment was brought in, pieced together. They utilize fan arrays, evaporator cooling humidifier. I'll be calling that ECH from now on. They use a DX coil, and then they have a relief fan that all this stuff works together to maintain temperature, humidity, and pressure requirements. Our electrical rooms, so our critical area, they utilize crack units to maintain temperature. We have a core area there as well. It has a BDF room, an MDF room, an IMPO room, and the design airflow for those are about 100,000 CFM. And 2 industrial water plants delivering water to adjacent data halls and core area for the ECHs. Your non-critical rooms, admin, restrooms, corridors, they won't have redundant systems. These critical areas, they will have redundant systems. So while we're testing, I'll be covering during the build out and then also renovation. So during our renovation, we be very careful about what we're turning off, just because everything we need kind of our N+1. We need to have always a minimum amount of equipment on. All right, let's go real quick over the layout. This is 2 buildings together in kind of an H shape, 4 data halls per building. We have electrical room serving each data hall. And we have a core area where our IMPO, MDF, and BDF rooms are. Then there's an admin kind of in the middle. I'm not going to really talk about admin today. That's simple DX, pretty straightforward, VAVs, air handlers. And then there's an IW plant that serves the adjacent data halls. All right, kind of a top view looking at it. We have outside air. So air is coming down toward you right now. This is the top view looking down. We have our outside air coming in. This is your mixed air. We have bagged filters right here. This is leaving the filter, going into a DX coil. Leaving this DX coil, going into our ECHs. Leaving the ECHs, going into our fan arrays, going down into supply shafts. So this is the penthouse, which this air then goes down the supply shaft to the first floor. And then depending on pressure requirements, these relief fans will come on. All right, same thing kind of over again. We have our penthouse where all our equipment is at, our first floor where all our servers are at. Then you have a return relief plenum. Airflow comes in, goes through outside air, hits the filters, goes to the DX coil, hits our ECHs, goes to our fan arrays, goes down, goes through our airflow monitoring station, gets to your cold aisle, distributes out, comes out hot air, and then whether, depending on what we need, relief or full return, our air will then go back to the penthouse, either up through our air handler or up through our relief fans. Cool. So outside air and return air dampers, what are we doing as a tap company looking at these things? So ideally, we love that free cooling one, 100% outside air. Just going to make sure that our economized signal will modulate the outside air and return air dampers to maintain a supply air of 65 to 80. What we're doing, if outside air conditions allow, we'll test the data hall at 100% outside air to test the full operation of the relief fan. Very careful, since it's 1.17 million CFM, to slow down on hitting the gas on that. We had a gentleman that turned the air handler on a little too quickly, and it blew the doors open and put a hole in the wall. And we'll also calibrate the temperature and humidity sensors. All right, DX coil and bypass dampers. So the function that we were for DX coil was dehumidification, pretty much only. So the bypass dampers are going to whenever one DX coil needs to come on, bypass dampers will modulate to a differential pressure set point across the coil. That way we have ensure enough airflow is going across that coil. It's very important testing these sensors out. Otherwise, you could be freezing your coil. You'll get a low pressure or high pressure alarm back at your condensing unit. So capacity test of full operation. Very important we have correct outside air and entering conditions. Since this is set up for kind of a failure mode, you're going to have to get a lot of heat and a lot of airflow across that coil in order to get every single circuit going. There's 4 stages, 2 circuits each. We're going to ensure all the DX bypass dampers modulate together, calibrate temperature and DP sensors, and test all DHUM SOO. All right, ECH. You say, Paul, that looks like a swamp cooler. Well, that's basically what it is. This is basically a swamp cooler. We have auto flow devices, maintain water flow each ECH. ECH will also enable if discharge air falls below 20% humidity, and then bypass dampers will modulate close to allow more airflow. So I want you guys to focus on kind of how that shape is, because right after this is going to be our fan array. So as we look at our fan array airflow measuring, it's going to be very important for us when we're doing our testing that these dampers are actually closed. Something I really want to hit on here is we continually, no matter what, every time we started our testing of auto flow devices, taking the pressures across it, we always had debris. No matter what, they already flushed the system. Every single time we'll always have debris. So we actually asked the mechanical contractor to put a step in a checklist when they do their startup to clean it out probably 2 or 3 times just to ensure all the debris gets out. So yeah, we test all the cooling and humidification sequences as well. All right, supply shaft. So that supply shaft there has a very recognizable airflow monitoring station that is gold. That's all I'm going to say about that. So the supply shaft airflow monitoring stations, each a 96-inch by 118-inch supply shaft opening. The control system actually looks at this airflow monitoring station sums of all 15 to make sure that they can meet these demands. So at our high end of 1.17 million CFM, that's our low demand of 7.5 megawatts. We verify correct altitude, duct area, flow gain, other parameters because they never come in. They never come in correct. So if you're going to test and balance your own data center, make sure you check this. This is very important. Any of that stuff is off, and you're going to be a couple % off of what you expected. We actually use a bell grid and do a velocity traverse 12 inches underneath that airflow monitoring station. So it's kind of high up there in the air. So we're standing down here, and we used to get a one-man lift to get up in there, but it took a lot of time. So we got a painter stick and fastened our bell grid onto that. So we're able just to stick it up there, and it takes us about 5 minutes to do a shaft. Relief fans, again, their function is pressurization. They're maintained at 0.05 in the space. We'll record sag pressures and test it at full capacity with the bell grid. Ensure all the dampers operate correctly. All right, the fan array. This is where I'll get excited now. Okay, so kind of looking down on the left side is the inlet of the fan array. I want you guys to pay attention to how this ECH module right here goes into the fan array, and then this is the outlet side. These are your supply shafts. They just have construction media over right now, so normally it's just grates going down. Like I said, I think your airflow monitoring station is about 60 inches down, somewhere between 6 to 8 feet. All right, so 12 fan arrays, 15 fans each, 180 per data hall, 1.17 million CFM. So this is what we're looking at per fan. And fans 5 and 11 house an airflow monitoring station that measures the DP across the fan cone. They take the average of those two fans, times it by 15 fans, and that's your fan array total CFM. You add all those up, obviously, that would be what you have in the whole data hall. So what we started doing, was measuring those fan array airflow monitoring stations at 54 hertz. We would take a duct sleeve, attach 27 by 27, 60 right up to it. Because it was so long, we had to put a sawhorse underneath it, and we did a pitot tube traverse. I think we started out doing fan 11, fan 5, and then we kind of learned that we had numbers were very close, so we just did fan 11 because getting fan 5 was about 12 feet off the ground, so it was kind of not too safe. Verified the calibration of the fan array airflow monitoring station then at 45 and 36 hertz. Using this method between our traverses and those fan array, the calibration of the fan array airflow monitoring station, 93 out of our 96 fan arrays across 2 buildings were within 5%. Cool. Feels great, right? Warm and fuzzy. You can go home at the end of the day and feel like we were doing a very good job. We also did our airflow monitoring station recorded the airflows in the supply shafts and took statics across the whole system at 30%, 60%, 85, and 100 in failure. So again, cool. Feel good about the 93 or 96 fan arrays. We're all within 5% between our traverse and what the calibration on the fan array was showing. But the supply shaft airflow monitoring stations did not agree with our measurements. At higher speeds above 85, the totals would be within 10% of the 2 airflow monitoring stations. At lower speeds, we were seeing all the way from 15 to 37% off. So what did we miss? Because our traverses from 54, 45, and 36 in the middle told me we were within 5%, but what are we missing at the lower end here that these were starting to go away from each other? So there's a couple things. Another group came in, started checking fans, and we noticed that there was, not just at a site we are at, but other sites around the country, we had problems here with an excessive gap. When they were installing fans originally, they basically put it in there, ran it up, made sure it didn't rub, and then that was their sweet spot. They didn't have a standard for how far they were putting the fan to the fan cone. So the manufacturer was told to add bracing and come up with installation guidelines. Third party found issues with the airflow monitoring station, so that also accounted for some of the discrepancy we had there. Wasn't totaling airflow correctly at lower speeds. And then we were told that we needed to measure every single fan, not just the one with the airflow monitoring station on it. So let's talk about what that means for us. So we were given this, and they said a group came in and measured every single fan, and this is what they were seeing. So we have a couple air handlers here. This one up here is 73% speed. This one here is 57% speed. Every single fan in here was all over the place. And they were asking us, hey, we need you guys to also do this every single time you tab. How are you going to do that? So let's talk about the problem here. It's not very safe to do a traverse that close to the fan. You have tubing, you got to get a sawhorse underneath the ductwork. You got to get on a ladder if you were to do it at even the higher rows. So the owner came to us and said, have you considered using the airflow monitoring station that we use in our supply shafts, put it into your duct sleeve, and read it out that way? I said, well, I don't know. I don't think it's industry standard. He said, no, is it possible, though? Sure, it's possible. We'll see. So we sent this to a sheet metal guy. We have here 2 sleeves that are put together. So when together, it's an airflow monitoring station sleeve and an extension sleeve. 30 inches airflow monitoring station is right in the middle. They asked us to reread 8 data halls in about 2 months after the bracing and inlet cone adjustments were made. So we built this test rig using duct sleeve, using the same airflow monitoring devices in the supply shaft. Prior to our use, we did a pitot 2 traverse. We want to make sure, like you would do with any other airflow monitoring station, we would check our calibration prior to each use. We were first told then we were going to use a duct jack and ladders to reach fans on the top 2 rows. We would actually later change that to just use a one-man lift. And then the guy who worked with me was a D1 college football player, so he can lift this. So this is our test rig built together. As you see here, it sits right on the fan. It's a 27 by 27. It's 7 rectangle here, and like I said, I think this is without the extension sleeve on it. We only used the extension sleeve we needed. We were verifying it with our traverse. We also did traverses without it on, and I believe later in the project we just ended up getting rid of the extension sleeve because our traverses were always true. So yeah, what we have here is the airflow monitoring station controller. Transformer right there is actually what weighs the most on this whole rig. So this was made out of aluminum. It was very light, really easy to move around, and we were able to do our work very fast. So a couple things I want to talk about here. So this is the first data hall we did. This was after their first adjustments. Pretty good, a lot better than that other graph I showed you earlier. I want to highlight looks like 4 fans here. Here. So we identified these as problem child. They went back, adjusted them, and you can see there. Bring it right up there nicely. But this last guy, that one, we had him adjusted, but it still didn't pull it up high enough, so we thought, okay, we have an issue here. So this is laying out the numbering of the fans on our previous chart here. At the bottom, these were fans, as fans go through 1 through 15. And what I'd like to draw your attention to is, okay. Okay, there it goes. All right, what I'd like to draw your attention to here is as the airflow goes into this fan array, down here very low, this right here, that's just a wall. There's really not a path for that airflow. I mean, it has to simply turn and go in. So these down the bottom are already going to be underperforming regardless because the inlet conditions is a lot different than what we have up here. What I'd also like to draw your attention to is I highlighted here the middle column of fans. So fans 2, 5, 8, 11, and 14. So we know our airflow monitoring stations, we're on fan 5 and 11. I don't know if you guys can tell, but every time it comes to that middle fan, it ticks up, right? So we're using the airflow monitoring station on our highest performing fans to tell us what we're doing for those guys in the corner. You know, it just was not, it wasn't ideal. That was where some of that 15 to 37% was coming into. Just another chart there. And you can see penthouse after penthouse, data hall after data hall, every single middle column of fan, it's much higher. So what are we talking here? Let's pretend our middle there is 1.0. So I laid out the fan performances after going through all our buildings. Down there in the corner, which is one of our fans we had earlier, it was very low. It averaged already, no matter what, after all the adjustments, 80%, 86% of what its middle fan was doing. So, and I guess for people in the future, if you're thinking about using an airflow monitoring station across a cone, be very careful about where you put it. Be smart about where you put it because you could be getting the wrong number fed back to you. I know I've seen airflow monitoring stations on the corners. I've seen airflow monitoring stations on every single fan, which works pretty good too, but I've also seen those not work at lower speeds as well. Future builds after the third building removed the fan array airflow monitoring station, because really all it was doing was, it didn't give us a number we felt good about, and it really just kind of, nobody really trusted it. The owner didn't trust it, we didn't trust it, so they removed it altogether. So during this 2-month project, we had to reread everything. They said, all right, we're going to also change your whole tab procedure. So instead of reading at 4 different speeds, we're going to have you read at 3 different spots at 100% airflow. So what we did is they had us read at the inlet of the ECHs a velocity traverse. We'll continue measuring all fans, okay. And so we read, using a Velgrid, read velocities right here to come up the airflow, read velocities at our supply shafts, and then read our airflow monitoring, or read our fan arrays with our airflow monitoring station. On the ECH readings that we did, the fan, we had to make sure our DX dampers were fully open, otherwise it would have been too turbulent. Oh, and then they also, we were, at the time, one of the only AABC firms testing for this client. They had other NEBB firms, and they were not, I believe, not even testing sequence. So they asked us to remove our sequence of testing. It was being tested by a controls group that made the sequence, then the controls group that installed it, and then it was tested during L4 and L5. So they kind of felt like it was an overkill for us to waste time testing something that's already been tested out. Yeah, tested by 3 other companies. All right. So with this change in tab procedure, we were able to identify all the fan inlet cone issues immediately. When we were doing our pitot tube traverses, it took about 8 minutes per fan. When we changed to our new rig, it took about 45 to 60 seconds. So we ended up using a one-man lift instead of a duct jack to increase efficiency. Talked about the painter stick earlier. And then the common issues that we were finding, we actually instituted those into startup scripts for mechanical and controls contractor. So these are some of the improvements we made during our fan array verification. The mechanical contractor improved inlet cone installation that adjustments didn't really have to be made during the last 2 buildings. I got very good at what they were doing. And then eliminating the SO testing allowed more time for us to focus on testing systems and sensor verification. So this is the last building we did. That almost looks like one pretty thick line right there. A lot better than what we first were told what we had in the data halls. So some more examples. This was comparing it to after their first, when they made their bracing and their cone adjustments. Our mechanical contractor out there this is night and day. And that makes it easy for us. We find an issue, it does take about, just if someone's available, it was taking about a day to 2 days for them to get it fixed. That's awesome right there. All right. Water. Over our last 2 buildings, all our 3 readings were within 4% of each other. Our first data hall we did out there in our first building took 72 days to fully test. The last one, we didn't know the best procedures, and that makes sense. You get to a site and you need to learn what we're going to do works best for this project. So that's one reason why 72 days seems a little high. we were recording equipment testing before the controls was even complete. That happens at other sites. If you can put something in hand and go get it done, that works at other places. For what we were doing, we just were stepping on each other, and then we were finding issues with our control. We were finding issues that we needed controls to be finished. Obviously, we were performing control sequence verification. That took some time. And then all trades are still learning best procedures to complete work. Our last data hall there took 6 days to fully test. So when you are an owner, a general contractor, a mechanical contractor, and you're getting repeated success, and we say, hey, we cut it down from 72 to 6 days, everybody's feeling pretty good. And that helps us out as a tab company because we're always the ones, we always get kind of squeezed right there at the end. We improved the fan array measurement process, implemented all the common issue corrections and mechanical control startup, wasted less time modulating fan speeds. We just remember measuring this at 100%. Removed the SO testing, and then our testing procedures were shared among all the other sites. A cool thing for working this client is they love bringing everyone together in the same room and saying, all right, tell us your ideas. They love listening to whatever people have to say. They want you to work together, and that's what worked for us here. And we were working with some NEBB firms, and one of the things I remember, we were talking about verifying our airflow monitoring station. We pulled out a pitot tube. One company pulled out a Velgrid. Another company pulled an airfoil. Everybody kind of gets up there and say, hey, this is how I think we should verify this test rig. So we get up there. My boss does a pitot tube traverse. They look at the results. The guy immediately walks out and goes, hey, we need to order some pitot tubes. It was pretty cool to see. I was kind of shocked they were using airfoil. I don't believe we have a whole lot of success usually with those. So, all right, we'll talk a little bit about the hydronic equipment testing. So what was great about there having multiple sites across the country, they had already an idea of what their system pressure needed to be. It made it a lot easier for us it took it out of our hands. So we made sure that the controls were working and that your pumps could get there to that pressure. All the pumping equipment and piping was pretty much oversized because everything is there set up for redundancy. However, we didn't have a procedure to do like failure testing of piping. And that's one thing I wish that we could go back and we kind of at the end figured out that was what that the engineer wasn't even thinking about. So your pumps come up, you have 2 pipes going back up to your data hall and valves all along the way. That way you can do any kind of maintenance on it. And we just never, that was one thing we never addressed and never really talked about. So also make sure to be present when pumps are being tested full flow for the first time. I remember walking into, because these are so large pieces of equipment, I remember walking into IW room and it sounded like someone was making concrete in there. And every single pump was at 60 hertz and every single one was cavitating. So please be present when your controls guy decides to run a pump up. As I was saying earlier, not only should we put pumps through failure testing, we should also I believe we should be starting putting tanks, piping, and valves through failure mode testing. We have overflown water basins at ECHs because we had partially closed valves that we just that were showing full open. During our testing of testing individual tanks, we had sediment sitting at the bottom of the tank. Got stirred up, and then it ended up in the ECH autoflows after 30 minutes. So that's another thing that I wish we could have told the mechanical contractor to keep an eye on. Oh, I realized what I did. I'm hitting the wrong button. All right, so tab and CXA, how is a good way to work together? CXA, I would say if you have a question about performing a test that might be off script, I'd talk to your tab technician. Usually when I have a set of data there and it looks great, I've probably tested that equipment 3 or 4 times, just to see, is it working like it's supposed to? So I also think it'd be good if CXA, you shared your test script with Tab, and Tab, we would share our procedures with CXA. Like I said, we didn't necessarily have a checklist at this project, and so they didn't really know what we were doing. And then I just think it'd be good to make sure we don't have any holes that are missed during the testing of this equipment. So I'd say for me over Tab, we got our CXA involved on unique issues. As I was talking earlier with our our fans in the corner, they were getting highlighted as problem fans, and we would have the mechanical contractor go back and check, and he's like, no, this is set up right. We don't know what's wrong. So we came up with a new standard to present to the client that looked at not only how the fan is performing versus that fan array, but how it's performing against other fans in the hall. So originally they say we want every fan within 10%, but if you remember the graph I showed earlier, those bottom quarter fans were already 86, 87%. So they were never going to get there. Now this standard is used across all the client's data centers. Also, which I think is interesting, CXA, if you find an issue during L4 in an area, let us know, because we could be in another area doing L3, having all the run of the place and getting to do what we want with the system. So if you find something, like an L4, let us know, as we will gladly perform that test to make sure it's either if it's an individual unique issue or if it's something that's going to be a consistent issue. All right, so we're not all going to do data halls. So some of the lessons learned from this case study that I would say could apply to other Tab companies, could apply to other projects, is checking for consistent fan spacing at the inlet cone for consistent results. If you're using an airflow monitoring station like our fan array one, make sure it's not performed on a higher performing fan. Especially if you have outside air kind of tied into that airflow monitoring station, what's outputting, it could mess with your pressurization of the building if you're thinking you're doing a lot more airflow than you think you are. And then I would check the calibration throughout the range of operating speeds. I think it's good to implement common corrections for issues into mechanical and control startups to save project time. So again, if you're doing a project where you have similar areas over and over and over, and we keep finding the same problems over and over, I think it would be smart for us to let everybody know in the room, and then hopefully you guys at CXA say, hey, put that in your checklist. Says, I think that we can work together and save time on that. As I said, compare testing procedures, so any unexpected scenarios do not arise during commissioning. And be able to adapt and learn from others to improve testing procedures. We felt very good about our 5% from between our traverses to fan array airflow monitoring station. We had our warm and fuzzies, but we had to sit there and swallow a hard pill that we weren't doing it the right way, and we weren't giving the client the best product that he needed. So, and if space allows, try building you one of those airflow monitoring stations. I think they work pretty great. All right, so we're at 38 minutes I see on here. Are there any questions? Yes, sir. Let me get you a mic. You want to? Cody back there is going to get you a mic.
So you were checking the individual air fan and getting a total for the fans by measuring those two fans, and that was 1 CFM total, and then you had an airflow station.
So yeah, the fan array. So we were
two.
calibrating the airflow monitoring station that was in the fan array. It was measuring the differential pressure across the fan cone, and so we calibrated it and checked calibration at lower speeds.
And the cone adjustment improved it, so they were consistent, but then the arrangement wasn't allowing the lower fans to get the right airflow.
That's correct, and that's why we adjusted between us and the CXA. Let's see if I can get back to it. We adjusted what was deemed acceptable to the client.
Was the airflow station always correct? And you were trying to get the fan arrays to match it?
So yeah, I mean, we had, again, the made a comment earlier about 93 of our 96 fan arrays were all within 5%. And then as we checked that at lower speeds, that was sticking for us. But again, we were measuring the higher performing fans. So when it was totalized, again, that fan array airflow monitoring station is taking the average of those two fan arrays, multiplying it by 15.
Mm-hmm.
So some of those fans, if we get back to it, they were, let's see, here we go. You know, you look at what we were doing on the outer columns of fans, 95, 96, that's how they were doing, that's how the airflow they were doing compared to the fan in the middle. So those two in the corner, 13 and fan 13, fan 15, they were never passing per the original thought of how we're going to say, hey, these fans are working right. So again, we then took the average, we compared each fan to the average of this fan array, and then the average of the individual fan, we would take we compare that airflow to the average of this fan array, and then also kind of looked at every single other fan in the data hall to see what the other fans were doing. All right. Does that answer your question, sir? Or do you have another thing? Okay. Any other questions? Yes, sir. Right here. So this one issue we were having is the procedure they were using in factory when they were setting up their fan, where it was a different table, I guess you would say, when they're balancing the fan, not the tab balancing that we do, but the balancing that they were doing on their rig as they were putting it in was different than what they were using out in the field. So they came. Well, yeah, so that was one of the issues that got addressed to the mechanical contractor. So they started making that adjustment. And as I said, as we got to the last two buildings, when we would check their work, they never had to adjust the fan again. So they did get better over time. We did get all the tab companies throughout the country that were working on this, all the mechanical contractors, all the controls contractors, and we brought them to Fort Worth, and we all had a powwow to come up with this best procedure. So it was one of the things that was talked about. Also adding bracing, that helped out a lot. So Oh, absolutely. I mean, they already had data centers in operation. This data center was in operation. So when they were making adjustments, they can only do one fan array at a time. During the actual construction, the new build out, they could do all their work at once. But during the Yeah, so they did. We weren't there when they were doing that thing, so they did have a standard that how far they could put that off of the cone. When they were originally doing this prior to the bracing, if it was rubbing, they would back it off. Yeah. Yes, sir. So when they came up with their standard, though, like I said, the last two buildings that we did, we never had to ask for a readjustment. All right. Anything else? Yes, sir, out there in the back. Yes. Well, it did have a filter skid. It cleaned the water, and we had a lot of PVC shavings that was getting to the ECHs. So even though the water was clean, and then when they were going through and putting glue inside the piping, that stuff was falling off, flaking off, and ending up in the autoflows. Yeah. We also had times. Another one is when they were putting all the piping together, they would have the actuators just closed because that's how they came from the factory. So if I went up to it to measure across that flow con, I could tell real quick based off my pressures whether or not that glue would come down and it would plug right there at that actuator. So, anything? No. Do we have any other questions? Any other questions there on the front row, sir? What's that? Yeah. There's a gentleman in this room I worked with on this project, so he could probably tell you the other side of this. Oh, matter of fact, you probably watched this. Derek DeJesus here did a commissioning of a Hyperscale data center powwow a couple years ago. Yeah, that's where I took this title from. So, any other questions? I think we're at 45 minutes now. So, all right. Well, thank you guys for coming in and sitting in and sticking with me.